So I'll be talking today, as my title indicates, about semi-classical gravity conceived of as an effective field theory, and the possible bearing that thinking of it in that way has on the information loss paradox. Um, I actually am going to do a bit more than that, as Enzo suggested I might. I am going to try to squeeze a little bit more into the talk than just what the title suggests. I will very briefly, let me see if this works. I will very briefly just say a little bit about what quantum field theory and curved space-time is. I'll mention a few problems that on their face may not seem related to the information loss paradox, but if, in fact, as we'll see in the discussion going in the subsequent discussion, these problems are directly related to the information loss paradox, and in particular, whether or not there are good grounds for taking the paradox seriously as telling us something of perhaps fundamental relevance to, or something of relevance to a deeper, more fundamental theory, a theory of quantum gravity. I'll then talk about the information loss paradox itself, and discuss exactly the way in which one may or may not, well, two ways at least, in which one may try to think of semi-classical gravity as an effective field theory and how that bears on the information loss paradox. And I'll conclude with a few rather, let's say, I guess to be completely honest, rather preachy and self-righteous remarks about how we should be thinking about how we as philosophers and as physicists should be thinking about all of this. Okay, so to begin with, very programmatically and generally, so general relativity is, as all of you know, it's one of our I'll say three best theories in physics. It's the theory of space-time and gravity developed by Einstein in the mid-teens, the mid-19-teens. It's valid from middling to largest spatial and temporal scales, and from near perfect vacuum to superdense matter, so far as we know. That is, I think, pretty widely accepted to be its regime of applicability. It infamously treats space-time geometry as a dynamical field in its own right. It does not include in its treatment of space-time geometry any quantum effects whatsoever. It's purely classical in that sense. And also infamously, it is quite promiscuous with regard to the kinds of causal structures it allows space-time model to have. And in particular, it allows, one does not have to get even very pathological with regard to the kinds of causal structures one considers before one runs into problems. Perhaps inconsistencies may be too strong a word, but certainly tensions with the kinds of causal structure that quantum field theory, or quantum mechanics, and in general, and quantum field theory in particular, as we know and love it, seems to require, seems to want. Quantum field theory, instantiated by the Standard Model in particular, is the second of our three best theories. It's our theory of matter and the forces that mediate interactions among material systems. It's valid, as far as we know, for at least in our current understanding, for mesomolecular, say, and smaller matter at the smallest spatial and temporal scales, and for highest and lowest energies. It assumes a static, flat space-time geometry. On our best current understandings, it does not include gravity. I think it's worth remarking that that doesn't follow from the previous statement, as sometimes I think people seem to think it might. For people have tried many times, and people still try to model gravity as a quantum field in a very straightforward, standard Lagrangian setting, introducing gravitons as the particle carrier for the gravitational force treated field theoretically, and that is that is all in the standard simplest setting. That's all formulated on the background of Minkowski spacetime. So the mere fact that quantum field theory seems to presuppose static flat spacetime geometry doesn't by itself mean that we're not using gravity, that we're not trying to incorporate gravity. But quantum field theory as we know and love it and actually use it successfully does not include gravity in the standard model. Quantum field theory also, of course, infamously admits extreme quantum weirdness that is in some ways, if not absolutely inconsistent with principles of general relativity, at least seems to be strongly in tension with it. And here again, I should try to be a little more precise. I mean, most of the talk is going to be very programmatic, very large, very global in scale. I'm not going to try to make a lot of very careful, very precise, very carefully detailed claims, but I'll try to be a little more precise now and then. And here, I think it is again worth remarking that the extreme quantum weirdness that really is problematic with regard to trying to fit quantum theory and general relativity together into a nice, harmonious, unified package is not necessarily entanglement. It's actually superposition that really causes the problems, and that will come out. That comes out really clearly in the case of the Hawking effect and the information loss paradox. Given that there is, in fact, it seems, again, if not outright inconsistencies between general relativity and quantum theory, at least a strong feeling of discomfort, perhaps distaste, that each has as an attitude towards the other, it is perhaps surprising to learn that there is, in fact, a consistent, rigorous theory of quantum fields on relativistic spacetimes, the algebraic or the axiomatic formulations of quantum field theory and curved spacetime. And in this framework, one fixes a background classical spacetime geometry. So one fixes the entire four-dimensional spacetime.
Erik?
Yes.
There is a small observation by Alexander about the superposition and entanglement. You can see in the chat, either Alexander, you can say directly.
Let's see. Where is my chat? Since I have since I have my slides on full screen, I'm not seeing the chat.
But entanglement is a special case of superposition. This is the chat.
So that strictly speaking, there is a very close relationship between entanglement and superposition. One can have entanglement in the sense of certain peculiar kinds of correlations in non-quantum theories. So it's not entanglement in the sense that that we normally think of as interesting or perhaps showing something very deep about the world is a matter of correlations between spatiotemporally distant systems. Superposition seems to at least in the sense that I worry about with regard to fitting it into general relativity has to do with a non-uniqueness, if one likes, of the state of a system at a given in a given localized space-time region. That's what really is the problem. That's really what's at issue with the problem superposition poses for general relativity, and not necessarily. So of course, general relativity doesn't care what kind of correlations there are anywhere between anything. As long as you can encode those correlations in the stress energy tensor, it doesn't care. That's why I say that entanglement doesn't really cause a problem for general.
Great, thanks. I didn't want to hold you up. Sorry.
No, please.
Good. Thanks a lot.
So, where was I? So, as I was saying, so in QFT on CST, in quantum field theory and curved spacetime, one assumes a fixed background classical spacetime geometry, and one assumes a quantum field that propagates on this curved background spacetime geometry as test matter. In the sense that whatever stress energy content the quantum fields may have do not affect the curvature of the classical spacetime geometry. One has to assume, in order to make the framework non-trivial, that the curvature of the spacetime geometry, in some sense or other, imposes constraints on the dynamical evolution of the quantum field. So it's test matter if you like, it's very the picture is almost Newtonian. That the spacetime geometry affects matter, but the matter. Well, no, that's gonna be way too complicated. Forget that analogy. That's a terrible analogy. Let's just say that the spacetime geometry affects the propagation of matter. the matter and its propagation does not affect the space-time geometry. There are, in fact, standard canonical and Lagrangian formulations of QFT on CST, but they're really messy and they raise even more mathematical and physical problems, many more mathematical and physical problems than just the nice, clean algebraic and axiomatic formulations do. And there are some, I should say that the fact that the quantum fields are non-interacting is not, strictly speaking, necessary. It's just what it's always done because we really don't know how to deal with interacting quantum fields in the algebraic or the axiomatic frameworks. There are a few results known in lower dimensions, but nothing of real physical interest. But freedom, treating these things as test fields is scary. We like to have all the moving parts in physical theories. We like them to bear on each other. We like them to constrain each other. We like to know how they interact with each other, not just act on each other. And therefore, we introduce a two-way coupling, a real interaction between the quantum fields and the space-time geometry. We shackle it with back reaction, and we do this by writing down what's called the semi-classical Einstein field equation, which is almost identical to the Einstein field equation, the classical Einstein field equation. The left-hand side still has the classical Einstein tensor, so we're still dealing with the space-time of the purely classical geometry. But the right-hand side now has, rather than the stress energy tensor of classical matter or an ordinary tensor, it rather has the expectation value of the stress energy tensor of the quantum field itself conceived of as a quantum operator. So we now have symmetric interaction. The geometry of the space-time influences the dynamical evolution of the field. The energy content, the stress energy content of the field constrains and informs the curvature of the space-time. But in contrast to quantum field theory and curved space-time, where we don't assume this coupling, we no longer have a completely rigorous mathematical theory. We have only standard. We have a number of standard formulations. We have Lagrangian formulation, S matrix formulation, path integral formulation, canonical formulations, Hamilton-Jacobi formulations, perturbative warts and all. We have problems of non-normalizability. All the problems that accrue to ordinary quantum field theory as we know and love it in the standard model arise here, compounded by the fact that we now no longer have a static fixed background space-time geometry. But nonetheless, just as in ordinary quantum field theory, the lack of mathematical rigor doesn't stop us from applying the theory in extremely precise, accurate, and very profound ways to give us information about the physical world. The hope, I take it, still is here as well. Well, okay, fine, we don't have a completely rigorous mathematical theory, but we know how to handle a lot of these problems already in standard quantum field theory. Let's see how far we can go using standard techniques, or perhaps generalizing standard techniques, and see what kinds of physical predictions we can extract from the semi-classical Einstein field equation. But this does raise the question, this still does raise to me a very deep problem. If one likes it, is the most fundamental question in this entire area for me. Because general relativity is a mathematically rigorous theory. How does the sober, rigorous, and precise Apollonian convocation of classical Lorentzian geometry and the exuberantly inexact and informal Dionysian fandango of quantum field theory come into mutually fruitful contact so as to give the joy of material content to the former and the restrained discipline of consistent structure to the latter? This problem, I hope to convince you by the end of this talk, lies at the bottom of every other problem that we will discuss. How do these two radically different theories come to fit together at all, much less to do so in a way that we seem to think gives us very deep and novel insight into the structure of space-time and the conceptual structure of space-time the conceptual nature of matter, and how our conceptions of both may need to be transformed in constructing a deeper, more fundamental theory of quantum gravity. Because that's exactly what this framework, we hope this framework will provide us. And this question, I think, is especially urgent in light of the fact that these theories are prima facie in severe tension, if not inconsistent. And yet black hole thermodynamics, which is formulated in the framework, either if one isn't taking back reaction into account in quantum field theory of pure spacetime, or if one is trying to be more sophisticated and take back reaction into account, is formulated in semi-classical gravity. Black hole thermodynamics is the most widely accepted, deeply trusted set of purely theoretical propositions in physics. I mean purely theoretical in the strictest sense, as in having no known empirical counterpart whatsoever. It's trusted so deeply that it's seen as the best guide to trying to construct a theory of quantum gravity. And as I intimated, all of this with no empirical access, much less in any empirical support. The investigations that take place in these frameworks are necessarily speculative in a way unusual even in theoretical physics. They are technically sophisticated, and technically sophisticated questions, physical questions, are inextricable from subtle philosophical considerations that span ontology, epistemology, and methodology, again, in a way unusual even in theoretical physics, because there is no constraint whatsoever imposed by experimentation or observation. No constraint imposed whatsoever by any empirical data. We take our two extraordinarily good theories in their restricted domains in their restricted regimes of applicability, which are very widely separate from each other. Each is very deeply entrenched, very well understood in its respective regime. We try to combine them in using general principles that seem, for whatever reason, plausible to us. We then try to extend that combination into a regime that we have never had any empirical access to, and very likely will not have any empirical access to for a very long time, if ever. Why do we trust this? And yet, it is a very, very, very unusual physicist who expresses anything more than token skepticism about black hole thermodynamics. I find this state of affairs deeply, deeply puzzling, and in some ways even troubling. So what are some of the problems that these frameworks face? Well, as I've already intimated by the way that I described why there's prima facie reason to be skeptical of the two frameworks. It's not clear, first of all, what the regime of applicability of semi-classical gravity is supposed to be. The regime of applicability of effective field theories generally, and just looking ahead, I'll explain a little later in the talk what I mean when I say that semi-classical gravity should be thought of as an effective field theory. But for the moment, it's enough for us just to know that the regime of applicability of effective field theories, where the effective field theory is expected to break down, where the effective field theory is expected no longer to provide an adequate and appropriate model of the phenomena it's intended to represent, are normally subscribed by energy scales or spatial and temporal scales. When the energy scales get high enough, when the spatial scales get small enough, not always either of those two, but those are very standard cases. But that actually is not the case here so far as we know. Here, the most severe circumscription is imposed, in fact, by the coherence of the state of the quantum field, which has absolutely nothing to do with the energy scale or the space or any spatial and temporal scales. I'll quickly sketch a rather evocative example that shows what I mean. So let's say that some extremely diabolical scientist has burrowed near the center of the Earth and has set up an enormous bomb, such that if the bomb explodes, it will completely rupture the Earth. Large chunks of Earth. Yes?
There is a question.
Excellent. What is
it? On empirical prediction connected with inflation. Perhaps Who is who asked?
Yeah.
Dan.
Daniel, if you want to pose the question, you can unmute yourself and pose the question.
Yes.
Direct.
Hi, Eric.
Yes.
When you mentioned that there is no empirical access to that regime where we use gravitation and quantum field theory and curved spacetime, aren't you ignoring the predictions of inflation that are so, are claimed to so successfully account for the emergence of structure?
That's an excellent point. Thank you. So the reason why I don't include that yet is because one, it's not it is the only reason we think that that we're in something like quantum field theory and curved space time, because or more generally semi-classical gravity to produce, say, the spectrum of anisotropies in the cosmic microwave background radiation, which is I'm assuming the kind of thing you're talking about. The only reason that we have to think that is what we're actually using is, to the best of my knowledge, none of the calculations that are done to produce the anisotropies in the spectrum are not full calculations in anything like semi-classical gravity. They're almost always one uses effectively a classical field for the inflaton, and then at the end, after one engages in the calculations, one tries to take quantum perturbations into account of the classical scalar of the classical inflaton field. But to the best of my knowledge, there have never been any.
We have a paper 2012 that does precisely that, treats all the inflaton field and its fluctuations or its perturbations in quantum mechanical language, and all classic and GR, all the metric in exactly classical language.
So I'm not aware of that. I'll have to look at that. Thank you very much for pointing it out. I would still be very, for reasons that I will get into later on, I am still worried about treating that as direct empirical access to the regime, to the relevant regimes, or treating that as treating that as an observation based on a prediction of the framework. I think that the reasons why I have those qualms will be clear later, will become much clearer later on in the talk. So if I don't address this worry, please return to it during Q&A, and we'll talk about it more. So standardly in effective field theory, the regime of applicability is, as I was saying, circumscribed by energy scales or spatial and temporal scales. In this case, however, the most severe circumscription is imposed by the coherence of the state of the quantum field. And what I mean by that is that when I say I mean coherence in something like the traditional sense dating back to Schrödinger, that the variance of the operator shouldn't be too large. The expectation value should, in some sense, be quite close to the peaks of the eigenvalues. So the kind of example I have in mind, which shows that the kind of coherence that's required for the semi-classical Einstein field equation to be applicable, has nothing to do with energy scales or spatial and temporal scales. The scientist builds a bomb at the center of the Earth, such that if the bomb goes off, it will rupture the Earth, large chunks going flying off in every direction. The scientist hooks the bomb up to a vacuum chamber containing an isolated neutron and a detector that will fire if the neutron decays, say, in the next 5 minutes. What the half-life of the neutron is, what, like 3 or 4 minutes? I always forget. Something like 3 minutes. So let's say that if the detector fires in the next 3 minutes, then the bomb will explode. If not, the bomb is detached from the detector and the Earth remains the Earth remains. No one expects that as soon as the scientist injects the neutron into the chamber and turns the detector on, that the moon will all of a sudden go veering wildly off from its expected orbit. But if you believe the semi-classical Einstein field equation, that's exactly what you should expect. Because as soon as the detector is turned on and the neutron is ejected into the chamber, the Earth immediately goes into a superposition of unexploded and wildly exploded. And that the stress energy distribution of exploded Earth is radically different from unexploded Earth. The moon will have radically different orbit depending on which field, which state it's probing. But no one expects that. So clearly, the semi-classical Einstein field equation is not applicable unless the quantum state is coherent in this sense one can make more precise than I've sketched. But it's not clear, as I'll discuss in more detail in a little while, how that kind of constraint can arise on any known understanding of effective field theories. So then there's the related problem of semi-classical coupling. What justification, if any, there can be for the form of the semi-classical Einstein field equation? Why should classical geometry couple to the expectation value of the stress energy tensor considered as an operator in the semi-classical approximation? I mean, expectation values in ordinary quantum theory standardly represent averages of possible experimental outcomes. So it's on the most naive, flat-footed reading, the semi-classical Einstein field equation seems to assume that classical geometry effectively acts as a continual measurement probe of the quantum field. That clearly cannot be what the equation means. That makes no sense whatsoever. Possibly one can, there may be interpretations of quantum mechanics in which one can try to make sense of that. Maybe on something like spontaneous collapse theories, one might expect something like this. I don't know. I'm now wildly speculating. Don't hold me to it. But at least on any standard understanding of quantum theory, the straightforward reading of the semi-classical Einstein field equation makes no sense. And you can't invoke the Ehrenfest theorem here to try to explain it either. The Ehrenfest theorem is just irrelevant. We're not talking about the classical evolution of the expectation value. We're rather talking about how the quantum field operator, the operator that represents the quantum field itself, evolves according to the principles of quantum mechanics when coupled to a classical geometry. Mostly, I think the thought is that the form of the equation is justified because the same techniques are used to derive the semi-classical Einstein field equation as, say, to derive the semi-classical treatment of phonons and their coupling to a classical fluid background. One takes an expansion of the relevant operators and power series of coupling constants. One uses a saddle point approximation. One truncates the first order, and there are very, very standard, well-known, well-understood techniques for deriving these kinds of semi-classical equations in which there's something like a classical background, there's something like a quantum entity that is coupling in some way with a classical structure. And what falls out looks very much like the semi-classical Einstein field equation. So I think people are really quite, people are not very worried about this. I think the idea is that, well, what's going on here is exactly what happens in other very, very well-known, very well-understood applications of effective field theory techniques in condensed matter, as we know in condensed matter physics, as we know it in quantum field theory, in treating quantum chromodynamics perturbatively, for instance. And why should it be any different in the case of gravity? Well, I'll have some things to say about that, why I find that unsatisfying later, but for the moment, I think this is why people aren't very troubled by this problem, although I am. One of the biggest problems for black hole thermodynamics in particular.
I have another question.
Yes, please.
When you first started labeling the theories that we have that are so successful, and you mentioned quantum mechanics and quantum field theory, you ignored the fact that those theories, without any way of addressing the measurement problem, are not really successful. They don't allow us to predict anything at all. So the success of those theories comes only if you address the measurement problem. And now you mentioned, these collapse theories on which you were kind of a little bit dismissive, or at least that sounded like, and that's one of the three paths to address that problem, without which, again, all the success that you claim for the first two theories is gone.
So, one, I did not intend to be dismissive of collapse theories at all. I think that they are really quite interesting and are absolutely worth exploring. I was not dismissive of them. I was rather merely only trying to say that if one wants to try to think of the fact that there's an expectation value on the right hand side of the semi-classical Einstein field equation, the most naive, flat-footed way of understanding that, according to standard quantum theory, is to think that something like, and now I'm not quote unquote, the gravity is acting as an effective continual measurement probe of the quantum system, since that's what one would expect. That's the kind of thing one would expect an expectation value to represent in ordinary quantum theory. I was saying I don't know how to make sense of that idea. Maybe one could make sense of it in something like a collapse interpretation. I don't know, because I haven't thought about it very deeply, and I certainly haven't thought about it enough to say with any confidence that actually would work. I'm only saying, so I'm not being dismissive of collapse theories at all. I was merely saying this might be a way of understanding that, but I don't want to commit myself to it because I haven't thought about it enough. The second point, I completely agree with you in one sense. I think that unless we solve the measurement problem, we absolutely do not understand quantum mechanics and don't understand why it is that quantum mechanics works. But you seem to say that without an answer to the measurement problem, we don't have an explanation of why either theory works. I don't agree with that for general relativity. General relativity is absolute. On my understanding of general relativity, it is utterly independent of quantum mechanics. And the measurement problem.
No, I meant quantum mechanics and quantum field theory.
Ah, okay, good. So yes, no, I absolutely agree with you on that. I think that any pretense to saying we understand quantum mechanics and quantum field theory without having an answer to the measurement problem is illusory. I completely agree with you. But insofar as the measurement problem is a problem for standard quantum theory and for standard quantum field theory, it's not a special problem for semi-classical gravity. It's still there, absolutely, in the background. But you can't talk about every problem at once, and no matter how ambitious and rambling your talk may be. So I'm going to put the measurement problem to the side. If you want to come back to it during Q&A, I would love to talk more about it. But at least for the talk right now, I'm going to try and put it aside. The final problem I want to raise for black hole thermodynamics in particular, this is not a problem obviously about semi-classical gravity in general, is that, and this is I think a problem that is weirdly not really talked about in the field at all, but I find it very troubling, that Hawking radiation is not generated by the microdegrees of freedom of the event horizon. You will 99.9% of the time when people talk about Hawking radiation, you will hear them say Hawking radiation is the black body radiation of the black hole. It's not. If you think about how black body radiation is generated for ordinary thermodynamical systems, I have a hot glowing lump of iron in my hands. I happen to be wearing some really good insulating gloves. The light, the electromagnetic radiation that the iron is emitting, the black body radiation, is generated by the wiggling and the jiggling of the iron atoms and the electrons in the iron atoms, and the characteristic ways that those atoms and the electrons are wiggling and jiggling and moving around and emitting lots of electromagnetic radiation is the reason why the temperature of the black body radiation we think is a direct proxy for the temperature of the lump of iron is precisely because the electromagnetic radiation is generated by the microdegrees of freedom of the iron. So the characteristic energy spectrum of the emitted electromagnetic black body radiation that encodes its Planckian temperature is a direct proxy for the physical thermodynamic temperature of the iron as encoded in the way that the material constituents of the iron is jiggling around. There's nothing like that in Hawking radiation. the Hawking temperature is the temperature of the quantum field as it propagates out to diffusional infinity. It is not generated by any microdegrees of freedom of the event horizon at all. So when the step that is taken, one has to take a further step to say that the temperature of the Hawking radiation is the temperature of the black hole by introducing, one has to make a further assumption, which is never made explicit in the context of semi-classical gravity or the context of quantum field theory and curved spacetime, to bring these two prima facie disparate phenomena, the dynamics of the horizon on the one hand and those of the external quantum field on the other, into explicit and harmonious relations with each other. Only then can one conclude that the temperature of the thermalized quantum radiation is a sound proxy of the temperature of the black hole itself, as determined by the dynamics of presumably its very own microdegrees of freedom. But it is exactly the lack of such bridging principles, as we will see, I think, that calls into question the importance of the information loss paradox. The importance in the sense that that it may be able to tell us something of relevant to the development of a fundamental theory of quantum gravity. So I'm not going to go into great. I'm going to assume, perhaps erroneously, but I'm still going to assume it, that people are more or less familiar with the information loss paradox. I'm not going to go into great detail describing it. I'll more or less only sum up what the upshot of the paradox is. This one slide is essentially my description of the information loss paradox. One has a quantum field in a curved space-time with a black hole, and one observes that the dynamical evolution of the quantum field takes one from a pure state in the past to a mixed thermal state in the future. That cannot happen with standard unitary evolution, the standard evolution of quantum theory without anything like collapse. But unitarity, we believe, is a fundamental property of quantum mechanics, quantum field theory, modulo the measurement problem. Therefore, there seems to be an outright contradiction between how quantum mechanics and quantum field theory is treated and understood when there are no black holes present, and how it is understood and treated when there are black holes present. There's a second formula, there's a second version of the information loss paradox, which is sometimes called the page time problem. And it's interestingly different from the first, from the standard formulation of the information loss paradox. I will again only very, very schematically and briefly say what it is and focus really just on the conclusion. So in the page time problem, one treats the black hole as itself a statistical mechanical system of quantum degrees of freedom, and studies how the Hawking radiation is entangled with the microdegrees of freedom of the black hole treated as a statistical mechanical system. It turns out very, very straightforward calculations then show that the emitted black body Hawking radiation, I'm now just using the jargon, even though in fact it's not clear that Hawking radiation is black body radiation. I'll use the standard way of speaking of these things. And the emitted black body radiation will eventually no longer be thermal. That's just a straightforward calculation using very, very standard, well understood, well entrenched techniques of statistical mechanics. There must be entanglement between the early and the late time quanta. But semi-classical gravity says Hawking radiation is thermal and that the thermality will not degrade over time. So this leads to a contradiction between treating the black hole as a statistical mechanical system and treating and deriving the Hawking effect using semi-classical gravity. Which is the correct treatment? It seems that one cannot have both. Now, I think that the arguments in favor of loss of unitarity and black hole evaporation, i.e. the conclusion of the standard form of the paradox, are really quite strong. Why? And now that this does, I think, directly bear on the question that Daniel raised about the measurement problem. Why all the fuss about loss of unitarity in the case of black hole evaporation, but almost no physicist you ask who really gets fired up when you say, you know what, black hole evaporation isn't unitary, and they just explode into, you know, they're enraged. But when you say, oh, by the way, it also looks like quantum mechanics is basically not unitary anywhere, because every time we do a measurement, it seems like we lose unitarity, they don't care. Why? And also, for that matter, if you're familiar with how effective field theories are used in standard quantum field theoretic context, you know that in fact it's absolutely standard for unitarity to be violated in effective field theories. Generally, the unitarity is violated when the systems start to probe the energy scales at which we expect the effective field theory to break down. And in fact, loss of unitarity in the effective field theory, standard effective field theories, is often heralded as the mark that the system is now probing new physics, i.e. physics that can't be handled by the effective field theory. And again, no one cares, because it's very well understood in this context why unitarity is lost. But correlatively, why is it that physicists feel confident that an effect predicted by what is manifesting effective field theoretic calculation, evaporation due to emission of Hawking radiation, can be trusted to reveal features of an underlying fundamental theory of quantum gravity? I really am deeply baffled by a lot of the way the discussion of the information loss paradox takes place, because it really is just assumed. I have never seen anyone even, I'm not sure I've ever seen anyone even try to explicitly address this problem. It is just absolutely assumed, unproblematically, implicitly, thoroughly, unquestionably, that if there's failure of unitarity at semi-classical level, that will automatically cascade down to a failure of unitarity at the level of a more fundamental theory of quantum gravity, or that the seeming irreconcilability of statistical mechanics and quantum field theoretic treatments of the black hole and the Page-Time problem automatically cascade down to indicate some failure at the level of more fundamental theory of quantum gravity. It's just not clear to me at all that we should assume that these conclusions we've reached in an effective field theory calculation should have such profound consequences, place such profound possible constraints on a fundamental theory of gravity.
Well,
a
comment? A
Please.
comment?
Mm-hmm.
I think the whole thing has acquired a new vehemency. I don't know, is that the right way to pronounce this word? After the acceptance, almost universal acceptance of this thing called the ADS CFT, conjecture, basically because the claim is that you have map theory in which there are black holes and in which gravity plays an important role, into a perfectly normal, simple theory in which there are no such objects and in which there are no gravitational effects, and therefore you shouldn't expect anything quote unquote strange. It's only because people believe so strongly, well, it's in part because people believe so strongly on this identification that the question has now acquired such a the characteristics that you described.
So I wasn't planning on talking about ADS-CFT, but since you raised it, I can say a few things. I think just as a purely sociological fact, I think you're right that is one of the reasons why people have become so vehement and so furious about the idea that unitarity might be violated. Because how could it possibly be? Look, ADS-CFT is telling us it can. I have two worries about this. One is that all the arguments I know from ADS-CFT, and that includes more general holographic kinds of arguments like Merle's holographic boundary unitarity argument. I find all the arguments to unitarity question begging, because it's explicit in Marolf's unitarity, holographic boundary unitarity argument. It's implicit in all the ADS-CFT arguments I've seen. There's always an assumption made in order to construct the dictionary that is supposed to show that the unitary calculation in the boundary theory just maps unproblematically to unitarity in the bulk theory. It's always assumed in the construction of this dictionary, implicitly, sometimes explicitly in the case of Marolf, that where in the bulk spacetime, at least wherever the spacetime is such as to be adequately modeled, classically or semi-classically, things are causally well behaved. You can't construct the dictionary without assuming a certain level of lack of causal pathology in the classical and semi-classical regimes in the bulk theory. But that's exactly what's at issue in the information loss paradox. There's a particular kind of the failure of unitarity in the standard calculations arises exactly because of a particular kind of causal irregularity in the global structure. A recent very beautiful theorem of Martin Lesord allows one to pinpoint it. In fact, allows one to say very, very clearly what exactly the causal property is that fails. It's causal continuity that is responsible for the non-unitary evolution. But if causal continuity fails in the bulk spacetimes in these ADS, CFT, and more general holographic arguments, you can't construct the dictionary. So that makes me worry that these arguments are first of all begging the question. Second of all, there's a certain kind of even if that problem could be addressed, and I don't think what I'm saying is not a knockdown argument whatsoever. It's just that current ways we have of constructing the dictionaries don't work. There might be a much better, more fundamental way of constructing the dictionary that completely avoids that problem. I don't know. I don't think anyone knows. But even if one could get around that first problem, there's still a certain kind of self-defeating. There's a funny self-defeating character to these arguments that ADS-CFT holography shows us that there is no loss of unitarity, because these people all want to take semi-classical gravity and black hole thermodynamics as our best clue for looking for a theory of quantum gravity. But black hole thermodynamics and semi-classical gravity tell us that unitarity is violated. You can't have it both ways. You can't say I'm going to use these results as my best guide for constructing my theory, but I'll only use those results that support the theory that I happen to like. Unless you have a more principled way of saying which results you're going to trust and which not, you are being ad hoc in the epistemically worst possible way. So
no, I was addressing the sociological question. Okay. I am not a defendant of ADS-CFT.
Well, I guess I went on quite a bit to answer a question you didn't ask. Oh well. I hope someone got something out of that. So but in any event, I actually do have a non-sociological possible reason why people get so fired up about the possibility that unitarity will be violated. And that's because in the case of black hole evaporation, as opposed to the cases of standard quantum measurement, and as opposed to the cases of how unitarity is lost in standard effective field theories, there's an articulated dynamical mechanism that directly yields the violation of unitarity. It's built into the calculation itself, which depends on this particular peculiar causal feature of the global causal structure of the evaporating black hole spacetime. And this is in clear opposition to standard effective field theory calculations, in which violation of unitarity is manifestly an artifact of the mathematical manipulations that are used to make the calculations tractable that make the theory an effective theory. And it's very clear, because we understand the physics of these systems, of these other standard effective field systems that we use standard effective field theories to treat. We know why the failure of unitarity doesn't reflect or represent anything physical in the system itself. Also, the failure of unitarity has nothing to do with the energy scale, as I remarked before. It happens at arbitrarily low energies. It can happen for black holes that are arbitrarily large, arbitrarily small Hawking temperature, where one does not expect the high energy modes one ignores in semi-classical gravity to be non-negligible. Wait, Is that right? Yes, that's right. There were so many negatives in that sentence that I thought I might have I might have gotten one wrong, but no, I think that's correct. So this may be one reason why people get much more exercised by the possible failure of unitarity here than in case of quantum measurement or in the case of standard effective field theories. And again, as I remarked in talking about the ADS CFT arguments, the failure of unitarity here again follows in the geometry of the classical spacetime background itself. It's not a property of the dynamics of the effective dynamics of the theory. And one can plausibly expect, given this very beautiful theorem of recent theorem of Martin's, that such global features should really be insensitive to any effects due to a theory of quantum gravity near the evaporation point, since those effects are appropriately localized in a small space-time region and don't affect the peculiar causal property, the global causal property that is responsible for the failure of unitarity. And it seems here, in fact, the onset of new physics that the violation of unitarity may point to is heralded, as I say, by complexity in the causal structure of space-time, which has to do with the fact that entropy is high, not that energy is high. That's looking forward to a discussion, which I'll get to in a moment, that probably somewhat cryptic remark. Well, as you may have gathered, I am suggesting that we perhaps should be more sanguine about the possible consequences of the information loss paradox than is standard in the community at large today. Semi-classical gravity is just an effective field theory. Why get fussed about problems in effective field theory? Well, before I go on, I've been talking about effective field theories the whole time. I probably should have had this slide much earlier in the talk. This is the first time I've ever given this talk, by the way, so I've given related talks, but this is the first time I've given this talk, and I apologize. I just realized I think that it was poorly designed. This slide should have come much earlier in the talk. But just to say now, to set the stage for discussing ways in which one might consider semi-classical gravity as an effective field theory. What I mean by effective field theory in this context is something like one constructs an explicitly approximated representation of phenomena using only degrees of freedom that are relevant for the scales characteristic, for the characteristic scales one is studying. So one generically leaves out, I'll just call them UV modes, because usually one is ignoring high energy phenomena, high energy compared to the characteristic energy scales of the phenomena one is interested in. And it turns out that just because that nature is really quite generous with us, we can very, very often, almost always, in fact, so far as we know, get away with ignoring what happens at very high energies or at very low energies when we're studying systems. The standard locution is you say the UV modes are integrated out. In other words, they're incorporated generally into something like a coupling constants that mediate the effective interactions at the relevant phenomenological scales. A very simple example. I think people don't usually think of this as an effective field theory, but it's really what it is. If you think about the coefficient of friction in the treatment of dissipative motion in just the most ordinary, simple case of Newtonian mechanics. You have a block sliding down an inclined ramp, and you include friction as a force acting on the block as it slides down the ramp. Well, that coefficient of friction you use to represent the force the dissipative force that acts on the block as it slides down the ramp is really an average. What that does is it encodes the averaged effect of intermolecular electrostatic interactions. But you just ignore everything that happens on the small spatial and temporal scales, and just aggregate them all together into the single scalar, and it works beautifully. And of course, the breakdown in such representations, when the representations fail, is exactly where you expect new physics to appear, the physics that your effective theory doesn't handle. So I've spent much more time, I realize, in the earlier parts of the talk than I intended to, and I'm almost out of time. So I think I'm going to, in the interest of trying to stick to as close to an hour talk as possible, I am going to skip over several slides and just mention at a very high level how it is that one might think of semi-classical gravity as an effective field theory, and why it should perhaps make one skeptical of the fundamental importance of the information loss paradox. So there are effectively two ways to think of semi-classical gravity as an effective field theory. Because the geometry is treated classically, in particular with no internal micro quantum degrees of freedom, I think it makes sense either to think of the classical geometry as a coarse-grained environment that the quantum field couples to. And in prima facie, one can in fact reasonably expect a Lindblad kind of evolution. You're essentially treating the quantum system, the quantum field, as an open system, coupling with a coarse-grained environment. That's a very well understood system to treat, and there are well understood ways of writing down master equations using Lindblad operators, which are generically non-unitary. So in this sense, one should perhaps expect that non-unitarity for quantum field evolution generically in semi-classical gravity, if one thinks of it as an effective field theory in this sense. The second way of thinking of it as an effective field theory is that what I will call the TBD gravitational degrees of freedom are integrated out of the coupling with the quantum field. And prima facie, then one perhaps could reasonably expect, for the most part, unitary evolution based on the analogy with other standard cases of constructing the effective field theory using this method. So there are I'll say that in the coarse graining, we treat gravity as a free statistical mechanical system, and then we coarse grain, and then we couple to the quantum field. It's really hard to see how this could explain coupling to the expectation value of the stress energy operator. And it's really hard to see how this could explain coherence to the quantum field state as a condition on the adequacy of the approximation. But it may perhaps shed some light on why unitarity fails, why in the approximation. In integrating out, we treat the quantum field's degrees of freedom as coupling with something like perturbative quantum gravitational degrees of freedom, presumably, whatever the micro degrees of freedom of curvature geometry are. We integrate out the interaction. We integrate out the interaction these TBD gravitational degrees of freedom. Then the coupling can't be with, but then we realize that the coupling can't be with fundamental quantum gravity degrees of freedom, because we don't expect those to couple with gross macroscopic matter, relatively speaking, quantum field theory matter, because generally speaking, we expect that in any quantum theory of gravity, matter will not be represented by an ordinary quantum field, the way that it is in quantum field theory and curved space-time or in semi-classical gravity more general framework. So in this case, once again, we see that we still get no relief from the information loss paradox, because the very way we're conceiving the semi-classical gravity as an effective field theory shows us that the degrees of freedom we're integrating out, which presumably are the same ones, I should add, that are relevant to the formulation and derivation of the page-time problem, can't be fundamental quantum gravity degrees of freedom. And that becomes particularly clear in the page-time problem, because in the page-time problem, one is explicitly treating the statistical mechanical black hole degrees of freedom with degrees of freedom of Hawking radiation, which are just photons. We don't expect fundamental quantum gravity degrees of freedom to couple with photons. So I'll just very quickly conclude that to recall the story that was told to justify the form of the semi-classical Einstein field equation, that its derivation in subsequent form mirrors that of other semi-classical phenomena like phonons. The problem is that, and the fact that it mirrored that the form of the equation and the derivation of the equation mirror what we know and understand in other cases, well understood cases, is supposed to give us confidence that that the framework is correct. But in the other context, because of all the background knowledge we have about, say, the solid state or fluid systems, for instance, including both theoretical and empirical experimental justifications, we know what the representation in the power series means physically. We know what the individual terms in the power series mean physically. We know what the saddle point approximation means physically, including its regime including the regime in which we expect the saddle point approximation to be valid. We know what truncating to first order means physically, and again, we understand when we expect it to work, when we expect it to be valid. Because of all the background knowledge that we have for these systems, for fluids, for solid state, for condensed matter. Because of all that, we have epistemic warrant for using, say, the semi-classical phonon model, both for claiming that we understand it and for claiming that it is a good model in the well-understood, well-circumscribed regime in which we expect it to work. We have epistemic warrant for using it as the basis for further knowledge claims that ipso facto already have some confirmatory support in virtue of being derived from a well-entrenched, well-understood semi-classical phonon model, for instance. We want to use the semi-classical Einstein field equation, semi-classical gravity, as the basis for arguments whose conclusions we want to have confidence in. We want essentially to use it as part of an evidential network to buttress the assertability of claims in black hole thermodynamics. But we have none of the entrenched background in semi-classical gravity that we have for phonons, say. I think we really must be careful in trying to use semi-classical gravity to draw fundamental lessons. And to be clear, to be absolutely clear what I am and I am not saying, and this is my last slide. I am not saying that we shouldn't use it as the grounds for speculative investigation. I am rather saying that we should be more critical, more skeptical, and more modest in our understanding of the epistemic warrant we have for it, both with regard to our understanding of it and with regard to our confidence in using it as the ground for further investigation. We really should be clearer on what our epistemic state is with regard to it. Thank you. I apologize for going a few minutes over.
We have 25 minutes more for Q&A. We can begin. Your presentation was wonderful and very stimulating. Obviously, I have plenty of questions, but I wait for no one have questions. Yes, Dan, go ahead.
Yes, hello. Well, first of all, thanks a lot for your talk. I must say I did my master thesis in sort of similar direction, so I'm very happy to hear similar points of view in certain aspects. I had a couple of questions. At some point, you said you never saw someone considering theories in which the effective theory has information loss, but the sort of fundamental theory is unitary. If I remember correctly, this is sort of advocated by Bernard Kay in his gravity matter entanglement hypothesis. I haven't looked into that much, but I was wondering if you have had any contact with it.
I'm sorry. Can you please repeat the claim that you're attributing to me? I didn't quite get it.
Oh, so at some point in your slides, you mentioned that nobody has shown or sort of shown the opposite of the fact that information loss on the semi-classical level cascades to the full quantum level. And I think a similar argument that doesn't need to happen indeed was made by Bernard Kay in his gravity matter entanglement hypothesis. And I was wondering if you have any, if you've looked into that or.
Thank you for that. So I did not mean, if I said that, I misspoke. I did not mean to give that impression. I didn't mean to say that I've never seen someone show that. What I rather said was, or wanted to say, was that in all the discussions in which people's move directly from unitarity is violated at the semi-classical level, therefore we have to worry that it's violated at the fundamental level. I've never seen someone who wants construct an argument that shows in the abstract why we should expect that if we don't have an explicit model of the form that Bernard, for instance, gives us. So, So absolutely, Bernard's picture is really quite interesting, and it has the great virtue of being actually completely explicit about exactly this issue.
Mm-hmm.
So, when an explicit model like Bernard's is not given, when people are just arguing about whether it's a good or a bad thing that unitarity is violated at a semi-classical level, there just always seems to be this absolutely implicit assumption that if unitarity is violated at the semi-classical level, it automatically means it's violated at the fundamental level. And I don't see that. The fact that it is, in fact, that it does cascade down in a proposal like Bernard's is incredibly interesting. But the fact that it cascades down in one particular proposal is not an argument that it must cascade down no matter how one can see, no matter what proposal one likes.
Okay.
Could I interject there?
Yes.
I think I am the Bernard that I was pleased to hear mentioned by the Erik and also Dan, who let me say hi to both of them. By the way, I've corresponded with you both, and
Mm-hmm. That's correct.
Erik on a couple of occasions. Yeah, I wanted to say anyway that yeah, well, maybe just to give a general plug, people might like to read my paper. I'll put a link in the.
You absolutely should, please.
I'll put a link in the group chat to a paper which I call, which has references to earlier papers of mine called the matter-gravity entanglement hypothesis, which I think addresses many of the questions that Erik was addressing and offers a solution to the information loss puzzle. What can I tell you about it now? I guess I would say semi-classical gravity isn't the right framework to resolve the information loss puzzle. It has to be resolved at the level of full quantum gravity, and I mean, relating to what I think you and Dan were saying, unitarity should hold at the level of full quantum gravity, but then won't necessarily hold at the level of the description of matter that's interacting with gravity. And the point is that matter and gravity will be entangled, and as time goes on, that degree of entanglement will increase. And so if you look at the dynamics of the matter alone, that will appear to be, say, in a formalism where you describe it by a time evolving density operator, then because it's in interaction with gravity and you're tracing over gravity to get the density operator for the matter, it will appear that the dynamics of the matter is non-unitary. So that's basically my resolution of the information loss puzzle. Maybe I could just say one more thing about that, if I could. I mean, I was pleased when, or let me say, I could relate very strongly to what Erik said when he said he finds it paradoxical or amusing that people always talk about lack of unitarity in the Hawking effect, but they don't mention that there's a lack of unitarity going on all the time in ordinary quantum physics because of the measurement problem, because of collapse of the wave function, right? And let me just say there's another side to that coin, of course, is people always talk about increase of entropy in the Hawking effect, and yet they don't seem bothered about increase of entropy in ordinary physics, and yet that is happening. And of course, that's the other side of the coin to lack of unitarity. That's happening all the time too, and it's what we call the second law of thermodynamics. And so I would say that I would say that the information loss puzzle is actually well, one version of the information loss puzzle is that how you reconcile increase of entropy with unitarity, okay? Because entropy is von Neumann entropy is a unitary invariant. so should never increase. I would say that the information loss puzzle at that puzzle, which is an aspect of the information loss puzzle at the level of entropy, is just a special case of a general puzzle, which is how can you reconcile the second law with unitarity? And I would argue, well, I do argue in this paper, I'll give you a link, that the resolution is the same for both, namely that entropy is not the von Neumann entropy of the total state of quantum gravity. So yes, I say that to resolve the puzzle of the second law in general, one needs to go to formulate things in terms of quantum gravity. I should have said that earlier. And entropy is not the von Neumann entropy of the total state. It is the von Neumann entropy of the partial state of matter, or another way of saying that, it's the matter-gravity entanglement entropy. And if you take that view about what entropy is, then there's no contradiction, so no paradox.
So Bernard, I should say that I have very deep sympathy with everything you just said, and I think your proposal is very interesting. Unfortunately, as I remarked to you in an email earlier, I think earlier today, in fact, I was speaking at a very programmatic, very general level in this talk today, so I couldn't go into details about all the different proposals that I think are really worth talking, that should be talked about in a much more detailed presentation and study.
Yeah, no,
I have a question for Bernard.
Okay, yes.
Bernard.
Yes.
Hi. Good to see you.
Good to see
Well,
you. Let me try and find your. Are you on video now? By the way, can I?
A very short.
I just woke up here in Mexico. It's much earlier, so I'm not.
Sorry, a very short question, because there is also Quechenberg that had a question for.
Okay. Well, so as you know, you and I, we agree in many things, but there is an item on which I disagree. We disagree, perhaps, and you were very emphatic on it. You said, at the full quantum gravity level, unitarity must be preserved. Well, why are you so convinced that this feature of that we have made good use of in quantum field theory, in what is an effective theory, in particle physics, in accelerators, will be preserved at that regime?
Sorry, what you asked me? Why do I think unitarity holds in full quantum gravity? Is that
yeah?
Well, I guess I'm just saying, if you assume that it does, but you make that other assumption that what entropy really is entanglement entropy between matter and gravity, then the information loss puzzle goes away. So
no, my point was just you were very emphatic regarding that it must hold.
Well, in this theory, that's one of the assumptions that it holds.
So if Bernard's theory is right, then it must hold. It's the right way to say it.
There is a question from Quechenberg. Go ahead. And then Benito.
Hello. Yes, my question was, why do you find the treatment of quantum of black holes for the unifying theory useful at all?
So I think that's an excellent question. I can tell you what I think. I can report to you what I think is the widespread belief in the physics community, and I can also tell you what I think, which actually is quite close to that. So first of all, black holes, I think, have for a very long time been considered to be excellent case studies for trying to understand quantum aspects of gravity, even completely independent of the Hawking effect, because they are arguably the simplest purely gravitational systems. They are the simplest non-trivial purely gravitational systems. So it's there's a sense in which black holes are much simpler than gravitational radiation. And so if you want to try and think about what how to treat gravity as a quantum mechanical phenomenon. It just makes sense to try and find the simplest, non-trivial, purely gravitational system, so you don't have to worry about what's happening with matter, and you can just think about gravity on its own. And black holes give you a perfect laboratory to do that.
So it's a laboratory in the cosmos, but not on the tiniest, minutest part of the particle, where quantum physics is explored usually.
Well, just because quantum physics is normally thought of, is normally used to study only the very smallest, let's say mesomolecular and smaller phenomena, doesn't mean it must be. If you have a certain realist bent of mind, I think that you will most readily believe that everything in the world is quantum mechanical, and we should be trying to use the ultimate goal, or one ultimate goal of physics, should be to try to understand everything in the world using some quantum mechanical kind of theory. But also it's important to realize in this context, even if you do just want to stick to your guns, stick to your empirically entrenched guns and say, look, quantum mechanics is really successful if they're very small. Let's just stick to that for the time being because that we know it works there. Well, general relativity is, in a certain sense, one can make precise a scale invariant theory. So when you study when you write down the Schwarzschild, when you write down the model for Schwarzschild spacetime, the M doesn't tell you how big the spacetime is, so to speak. The Schwarzschild model doesn't care whether you're talking about a black hole that's 10 to the minus 100 centimeters with Schwarzschild radius, or 10 to the 100 centimeters in Schwarzschild radius. So presumably, whatever you can, if you want to try to take quantum mechanical effects into account in treating a purely gravitational system like a black hole, starting with Schwarzschild it seems naively like a really good place to start.
Thank you very much.
Sure, and I will say one more thing about the Hawking effect. Why I think people take the Hawking effect to be hopefully a guide to quantum gravity. It's because it is, to the best of my knowledge, it's still the only example we really have of something that looks like a compelling case where general relativity and quantum field theory act together to give an entirely novel prediction, something radically unexpected. The case that Daniel pointed to earlier, using inflation to predict the anisotropies in the spectrum of the CMB, there's a sense in which that is a very straightforward application of a theory to make a prediction about a well-known, well-understood, already visible to us physical system. There's nothing surprising there. It may be surprising that it works so well, but it's not telling us something potentially novel and deep about the structure of the world, the way that a lot of people think that the Hawking effect is, because we somehow magically, by combining general relativity and quantum field theory, we get thermodynamics out. That was radically unexpected and novel. And so insofar as we're looking for clues to, we're looking for clues about how a deep theory might look, that seems like a really good place, that seems like a really good place to start if we're looking for something novel.
Thank you. It was just that I had doubts about it because Roger Ben was and then even changed his mind. So I didn't really trust one of them. Thank you very much.
Benito?
Hello. Can you hear me?
Yes, I can.
Yeah, perfectly.
Okay. Well, thanks. That's been a very nice talk. It was suggested by me. It was suggested to me by Bernard to attend the meeting, and I sort of signed up last minute, and I'm very happy I did. So let me just go. Perhaps, of course, I think one should expect the full solution to the black hole information loss puzzle to come from quantum gravity. But perhaps one could even, make an argument in semi-classical terms and as to how this should be resolved in some sense. So in part, I think part of the problem is we take Hawking's conformal diagram extremely seriously, and so this non-global hyperbolic diagram, and perhaps and this is a sort of back reaction. I mean, no one has really solved the semi-classical Einstein equations to obtain this diagram, and it's sort of it comes a bit from it's quite a speculative diagram, but nevertheless we have taken it very seriously in the past 50 years or so, 40, I'm not sure how many. But it is quite possible that perhaps if one could solve semi-classical gravity as a full dynamical system in the sense of initial value problem, it is quite possible that you would not get this diagram, and that in fact you could not get a non-globally hyperbolic spacetime out of initial data in classical gravity coupled to quantum matter through the stress energy tensor, expectation value, and so on. So it is quite possible that this diagram wouldn't come out. And I think there's this there's basic intuition that could tell you that perhaps this diagram doesn't really exist, which is of course that the radiation that comes from the black hole, which as you have well pointed out is photons in some state, particularly some thermal state and so on at Scribe plus, it keeps getting hotter and hotter as the black hole becomes smaller and smaller. And presumably, when the black hole evaporates, this is unboundedly hot, such that the energy on Scribe plus is so big that you should develop perhaps a singularity there. But fully I'm not appealing to any loss of unitarity in the sense of collapse and so on, or any modification of, or appealing to quantum gravity, but perhaps even in the semi-classical language, one shouldn't really trust this non-globally hyperbolic diagram and expect a singularity to form at perhaps at Scribe plus, and then get some sort of cosmic censorship kind of argument that could presumably also resolve the paradox without resorting to too much modification of canon, let's say. I don't know what it's just that.
So I mean, what you said I think is very interesting and very suggestive. But there is, to my mind, there's to my mind a prima facie problem, which is that let's try and think of ways not to take the standard black hole evaporation conformal diagram seriously. Well, you're gonna you basically, if you look at what's happening inside the event horizon, we have reason to think that nothing really crazy is going to happen until curvature, until scalar curvature starts approaching something like the Planck scale. That's very, very deep into the interior of the black hole. So at that point, if for a singularity not to form, for something like a singularity not to form, you don't have many options. If you want to continue the diagram, so to speak, you basically have to have something like an enormous pulse of effective negative energy in order to keep the conformal diagram from becoming in order to stop a causal pathology from developing, in order to stop the diagram from being applicable. And I don't know of any mechanism. There's no known mechanism, as far as I know, that can do something like produce an effective large pulse of negative energy to stop collapse from happening.
No, but I didn't mean that. I wasn't talking about the black hole singularity. So let's.
You're talking about a singularity at Scribe plus.
Yeah, I was thinking that. Well, you could have something like cosmic censorship because you see that the equations are so complicated that no one has really solved them.
Right.
So what we have is bit of speculation of how to continue this diagram. But perhaps one cannot really do that, because if one really tries to solve the semi-classical Einstein equations, one finds a kind of unboundedness of stress energy. It's perfect, by this mental picture of how radiation gets hotter and hotter. To me, this is not entirely unreasonable, and it doesn't really appeal to pushing the solution to a realm that is outside of canon. It's something I've never seen discussed so much, but it seems that in this community, people have thought so much about it that perhaps you have something to say, or you've thought about it, but yourself.
I think what you're saying is essentially right. That there's no reason to expect that the semi-classical, that even if we knew how to solve the semi-classical Einstein field equation for an evaporating black hole, which you're absolutely right, to the best of my knowledge, no one has ever done with anything approaching thoroughness or rigor. If we actually didn't know how to solve it for an evaporating black hole with any kind of thoroughness, we would fully expect the approximation to break down before we reach energies that would cause singularities to propagate out to describe us. I don't think that there's anything that would suggest otherwise.